The final talk of this session will be given by Reinis Cirpons about his work on certifying the decidability of the word problem for monoids at large. No.
Thank you. Yes, so what I'll be presenting is joint work with Florent Hivert, Assia, Mahboubi, Guillaume, Melquiond, James Mitchell, and Finn Smith. I have to say, I'm very happy to be here. It's been a very lovely conference so far. I was especially happy at today's keynote talk because as a mathematician, I'm quite new to the formal proofs community, but as a mathematician, I do very much look forward to the day where AI gets so good that me, along with 99% of my mathematician colleagues, can just retire and give up mathematics completely. But until that day comes, we still need to do mathematics the good old-fashioned way. And here I want to first give a motivating example about the sort of data-driven approach that one can sometimes take to solve some mathematical problem. So you're presented with some problem, and what you do is you first collect some data. You look at small examples. Maybe you solve them by hand. Maybe you use a computational tool. Once you've done this, you look at your data, see, I don't know, maybe it's powers of 2, maybe it's some other known mathematical object. This inspires you, gives you some intuition as to what the general proof could look like. You then formulate the proof, prove it, and you're done. This is the happy path. I've had good success with this quite recently. I was looking to classify some maximal elements of a certain lattice. It doesn't matter too much what it was. But point being, prior to making a table, I had no idea what the solution could look like. And then using a computer, together with my PhD supervisor at the time, we were able to compute a table of numbers. And we were very happy because we saw numbers which were one-off powers of 2. Oh, excellent. OK, this gave us some idea. Maybe the construction has to do with finite subsets. This turned out to be the case. We were able to classify it. Everyone was very happy. On the flip side, we really need to be sure that we've solved the small cases correctly, right? If we made a mistake here, this is going to give us the wrong intuition. We won't really know what the solution looks like. We won't be able to prove it. Now, if you're doing 5 to 10 small examples, this is all fine. But what happens when there's 100, right, 1,000? Well, you better certify your proof or have a verified implementation of the tool you're using to compute them. And that's really the central thing that we'll be looking at today in the context of the word problem for in relation to monoids. How can we certify the output of mathematical, computational mathematical tools which themselves are not formally verified? Can we do this efficiently? Can we do this for thousands, even millions of examples? And in order to get to that, I should tell you about the word problem in monoids. Disclaimer, I'm a mathematician, so it pains me to do this, but I won't be able to talk too much about the mathematics, but it's really beautiful. So I would like to point you to the wonderful survey by Carl Fredrik Nieberg-Bråde, which goes much more into detail than I will be able to today, if you want more of the mathematics. So the word problem. Assume we have 2 elements, A and B, in some set M, which is equipped with an associative multiplication. We know that a certain equation involving products of A's and B's holds. So in this case, BAA, BA equals A. We want to prove some slightly more complicated equation that may or may not hold. Or in this case, it does. So what do? Well, we spot that the left-hand side, BA, BA, occurs as a subword. We replace it by the right-hand side of this equation. We repeat this once more until we get a trivial equality, which holds. This is, in essence, what the word problem is about. So what we just saw is an instance of a presentation. So the elements A and B are what we call generators, and the equation BA, BA is the relation. So in general, the word problem for a presentation, that is to say, a pair consisting of a set of generators and a set of relations, is the question of deciding whether or not a pair of words in the generators is equal modulo r. So modulo using these equations, these relations to rewrite. And it is undecidable in general. We'll be looking at two related objects where this is undecidable. One of them is monoids. So that is to say that the generators come from a set which has an associated multiplication and an identity. And the other one is groups, which are just monoids together with inverses. The question makes sense in both of these. Naturally generalizes, and it's undecidable in both of them. There are even some very small examples I can show you. So this is a 5-generator, 7-relation presentation, which has an undecidable word problem, and it is misleadingly simple, right? You wouldn't, if you just saw this, you might think, surely, but no, you cannot decide the word problem in this. And in fact, if you look at the smallest examples that are known to be undecidable, you find that for monoids, this has, there's an example with 2 generators and 3 relations, which has an undecidable word problem. And for groups, the same with 5 generators and 12 relations. Which leaves open the question, well, what if we restrict the relations further? What if there's 2 relations, 1 relation? So let's look at the very extreme case. What if we have a presentation with just a single relation, just a single rule? As it turns out, for groups, the problem is decidable. For monoids, it's open. So this is still an active area of research. And really, it's been open since the very inception of the notion of a presentation and a word problem some 100 years ago or so. So what can we do? Well, before I joined this community, I was a computational semigroup theorist. So we thought, why don't we use the computer to gain some insight into this problem, as I just mentioned at the start of the talk. So let's try find maybe the smallest example where we don't know how to decide the word problem, right? So the smallest 1-relation presentation where we don't know how to decide the word problem. And to restrict the space even more, let's just look at a binary alphabet where both relation words don't exceed size 10. So this is about 4 times, so this is about 4.2 million presentations. And previously, this had been done in 1989, but they're restricting to u and v less than or equal to size of u and size of v less than or equal to 6. So that's about 10,000, right? So a step up. There are immediately some symmetries we can exploit. So very simple thing, if you swap u and v, clearly that won't change whether you can or cannot decide the word problem. And this allows us to reduce the search space to about 52,000 presentations. And then another result from theory allows us to reduce it even further. So Adyan and Oganesian actually show that for any 1-relation presentation, there exists one with a binary alphabet of this very particular form, which we call left cycle free. And furthermore, this theorem, there exists one of this form where the word problem reduces to the word problem in one of the 2 monoids of this specific form. And furthermore, this is all constructive. So we can actually find the exact presentation that it reduces to. We've also implemented this. And it even is non-expansive. So the relation words that you get afterwards are shorter than the ones, or shorter the same length as the ones that you began with. So this halves our search space once more. So then we implemented in Python, in C++, and in other tools, various criteria of decidability. So for example, if one of the relation words is empty, it is known from theory that the word problem is decidable. And it's very easy to check if a word is empty. You can just compute this. So we implemented that in Python. And all the examples on the right-hand side, so 1 through 7, are sort of polynomial time checks that come from mathematical theory. So for any given presentation, you could check whether one of these holds in polynomial time. All the ones on the left-hand side are more complicated. These are various computational tools, really general purpose, some of them, which may not terminate on all inputs. So they're significantly more difficult to run, and it takes significantly more time. With this computational toolbox, we were able to solve the word problem in all but 260 cases. And a majority of the time, so a majority was covered by known mathematical results, but these didn't take a lot of time because they were polynomial time checks, as I mentioned. And the majority of the rest of them were taken by Knuth-Bendix, which is one of these algorithms I just mentioned, which is a semi-decision procedure, really, so it may not always terminate. And so let's take oh, yes, and the total time spent for doing this was 6 days and 14 hours, and 6 days and 7 hours was spent on Knuth-Bendix specifically. So we should take a closer look at this, right? If someone wanted to reproduce our results, well, that would be the sticking point. So what Knuth-Bendix does, roughly speaking, is we start with a presentation. We enlarge it by doing something known as critical pair resolution. And then we check if this expanded presentation satisfies a certain condition known as local confluence, also a polynomial time check. If it does, that's good. We have a normalization procedure which solves the word problem. If it doesn't, well, go back to square one and do this over and over again. You can see why it may not always terminate, but when it does, it's incredibly useful. It solves the word problem. We can check whether a monoid is finite or infinite. There's also some applications to low-dimension homotopy and so on. Algorithm is very widely used in computational semigroup theory. It's implemented in all different computational algebra software packages, GAP, Magma, KBMag, libsemigroups, which is a C++ library, and so on. We use the libsemigroups version because that's the C++ library we developed. Now, a formalized implementation of Knuth-Bendix is pretty hard. The implementation in libsemigroups itself is over 1,600 lines of C++ code. And it's very performant. If we implemented it from scratch, maybe we could do a formalized one, but maybe it would be slower, not as great. So what we do instead, in order to certify our results, so we don't need to recompute this, or so that people could trust our results more, really, is to take a trace, a computational trace. That is to say, we look at all the times that Knuth-Bendix added relations to our presentation, and we build a formal certificate from this. So this is roughly what it looks like. So we start with the presentation on top. We apply Knuth-Bendix plus some heuristics. We arrive at the one at the bottom, which has slightly more relations. And then we formalize. So to the left, you see the Rocq statements defining each of these presentations. And then a proof certificate for this run of Knuth-Bendix looks roughly like the following. So we have some lines which describe adding a generator, some lines which describe adding relations, some lines which describe removing relations. Each of these is justified by a certain rewriting sequence using the current rules in the presentation, the current relations in the presentation. In general, for the other computational methods, the story is quite similar. So we take a computational method such as Knuth-Bendix, the small overlap oracle, anything else we've implemented in Python. We use it to generate an informal certificate, as we call it, or really this is just a computational trace. Put it all together in a proof database, and then we can use it to do all kinds of things. So we have some Python checkers which just informally look through the trace and check that it's well formed and isn't obviously wrong. We can use it to generate some human readable proofs. And what's most relevant here is we can use it to generate really Rocq certificates, really Rocq programs which, when run, certify that the computation was correct, that we got the correct answer. And these certificates can get really large, thousands of lines. And we really need to consider efficiency for this formalization. So some of them use rewriting, and initially we did not have an efficient rewriting mechanism. We just did this naively with like a quadratic matching algorithm. This was improved by using tries, really in Rocq, to speed up the proof. And then we're also users of native compute, right? So, which allows us to do normalization much more efficiently than without. So here you can see it's something like 10 to 20 times faster to use native compute than not on some select examples. And so together with all this, we can really run all of the proof certificates in Rocq in about 7 hours. 2.5 of these hours are spent really just parsing the presentation definitions, with an additional 4.5 hours needed to check the certificates themselves. Here are some of the results of our formalization. So this, here we have the type of the certificate. So this is the sort of the name of the Rocq constructor used to construct the certificate, how many of those there are and how many of them are certified. That is to say, certified without any admitted theorems in the middle. We had to admit some things, but as you can see, for complete rewriting system, which is the Knut-Bendix case, all of them are certified. This is like fully verified and implemented. All of this is available on GitHub. This library was primarily developed for the one relation monoid word problem project that we had, but it can be used more broadly. As I mentioned, Knut-Bendix can be used for checking whether a certain monoid is finite, and this is often useful to check if presentations that occur in published papers are correct or not, because sometimes mistakes can happen. It's quite easy to add one extra relation, remove a relation, miss something, and get something completely wrong. And for future work, we would like to formalize more of the underlying theory of one relation monoids. As I said, there are some admitted theorems. This will require quite a bit of effort, though, because it's quite a lot of mathematics that's gone into that. We want to improve the efficiency of our Rocq formalization even more, right? Use native arrays for tries and so on. We want to release the database for the mathematical community to benefit off of in the form of an online encyclopedia, so anyone can easily look up if a certain one relation monoid has a decidable word problem or not. And finally, we have the infrastructure up now, so it would be feasible to have a polymath-style collaborative project for solving the word problem in one relation monoids or something of that effect. And yeah, thank you.
I am interested in your use of native compute. Do you have intermediate data that is voluminous and that makes difficulty with communicating with native computation?
So I'm probably not the best person to answer this, because Florent here, one of my co-authors, was.
The certificate can be very large, like he said, like several thousands of Rocq lines. Yes. So what I'm not sure I understand the question. There is a lot of time parsing certificates and yes, just compiling them, but we all compile them natively, and everything is done at the native level. I mean, all the presentations are in separate files, which are compiled natively, which are imported. I'm not sure that answers your question, but... I can keep more precisely.
The reason I asked the question is because I used native compute before to compute millions of decimals of numbers. And the way native compute works is that there is no inputting of data. You input a program that is going to reconstruct the data. And and sometimes you get to the limit of the compiler because the program is too big for the compiler. Did you hit this kind of glitch?
Yes. So one trick that we use is to carefully. So we gather a presentation in batch, and the time of reading the batch can vary largely depending on the size of the batch. So.
Hello, I'm curious if either by looking at the proof certificate or the process of writing this architecture, if either this actually gave you insight to like the mathematical theory that people want to solve, or even if you haven't, do you expect there to be some sort of insight in these data that you collected?
Yeah, so. In fact, some of the decision procedures we arrived at here. There's a list of 12. Some of the later ones were, I don't want to say they are completely novel. Some of them are generalizations of existing theory. But we were only led to really come up with them, right, and use them to solve the problem because we found some instances that were really tough to solve with anything else, right? And so, for example, the 12th example, which is a rewriting system derived from Adyen's algorithm, we have a paper on that, and this is a sort of new result. It's really a rediscovery and a generalization of a old result of L'Allement and his PhD student, Janet Bro-Bousma, but sadly this wasn't developed further by other people, but yeah. So that, and also I gave a version of this talk at Leipzig this September, and at the end of this talk, I gave 2 examples of the smallest known, smallest presentations which we couldn't solve, right? And so a month later, we get an email from someone who says, I know how to solve them, and here's how, right? So there's already some interest from the community and people working on solving these hard cases. So I believe there has been some.
You also have some picture which shows some recursive regularity.
Yes. I didn't put that in here, but yes. Nice pictures.
Okay. While you're here, I also have a question about these conditions. I was a bit surprised that you include the timeout in the condition.
Yeah, well, so because Knut so these are.
I mean, if it would terminate, it would be okay, right?
Yes, but we were running these on a million, tens of thousands of instances, and so this is the only way we could keep the runtime low.
It's more experimental conditions, but if you would get these without the timeout, it would also be a decidability criteria.
No, because it may not terminate. So it sometimes does not terminate on some inputs, and in particular, you need to do some heuristics of adding generators and all that, which is kind of like a layer on top. I didn't have time to get into this, but even with the 10 millisecond timeout, it took 6 days, right? So you can imagine what happens when you double it.
So if it would terminate, you would answer this question, but it
yes.
would not be a decidability criteria. Sure.
Yep.
Okay, I think we can thank our last speaker and close the session for the coffee break.